All right, I'm going to attempt to teach this lesson, obviously via a video. I'm screencastifying here at Seneca because the lesson is so complicated that to do it live, I just think that people at home would really, really get left out. And even to do it live with masks and everything, I just didn't feel like that would be a good fit at all. So I'm still going to do video, even though maybe there's going to be a bunch of people here on Monday. I'm really not sure who will be here or whatever. So anyway, we're going to move forward. So we've been talking about how to write a series based on a function that we're given. So far, there's some stuff that we know. We know a few series already. We know 1 over 1 minus x is our most basic geometric series. The top number is the a, the bottom number is the multiplier as long as we have subtraction. So my series would be 1 plus x squared, and so on. We also know how to find series based on just this beginning spot. We know how to find the series this minus 1, that I would just subtract 1 from both sides and get this brand new series. We know how to substitute. We know that if I wanted to find the series 1 over 1 minus on even sine x, I could do that. I could say, well, I could treat it as geometric, or I could take the series that's up here and replace all of my x's with sine x's. That would be another way to write it. I also used, I can take derivatives and integrals of series that I know. And that's how I ended up with the series for the inverse tan of x. And that's how we ended up with the series for the natural log of 1 plus x. So somewhere we're going to have those written down in one spot so we can always look back. So that way I could always find the series for the inverse tan of 5x, because I could just replace all of my x's with 5x. But moving forward, like, this is a really limited list of things that we can take. We can find a series if we're given a function. So, we want to move forward and we want to think about some other big heavy hitter functions that come up. So we've got sine x. We're going to write a series for cosine x, and we're going to write a series for e to the x. And then we can write others, but these are going to be our main ones. We are going to write a series that you'll end up basically memorizing, or at least having on a cheat sheet near you. But the strategy that we use to get these series is a really, really important strategy. And it's called using a Taylor series. So if you go back to those notes from last week, we had ways to write a series. Number 1 was hope the series is geometric. Number 2 was substitute into a series that we already know. Number 3 was take a derivative or an integral of a series that we know to get a new one. Maybe there was something else, or maybe these were separate, because I think there were 5. But now we're ready for strategy number 5. And it's called use Taylor series. So the strategy called Taylor series will work to write a series for any function. So every function we can write a series for. Some are way more gnarly than others. But this strategy is it's simple in the end, but it's complicated to explain. It's not as simple as hope the series is geometric, or just substitute into one we already know, or hey, just take the derivative or integral of all the terms and we'll get the series I'm looking for. So that's what we're going to do today. We're going to look at what is the strategy called Taylor series. So to start talking about a Taylor series and what that is, I need to give you a lengthy explanation. So sit back, get yourself a snack, and see if you can try to follow what I'm going to tell you. So first, I'm going to talk to you about how to construct a series, and I'm going to use sine of x as my example. And that the construction of the series for sine of x will take us into a more generalized approach that we call Taylor series. So this is basically the proof that's going to lead us into what we actually have to do. So this section that I'm going to talk about now should be a sit back and relax and listen and try to just absorb and understand what I'm doing. You will not have to replicate this on your own. You really just want to be able to understand where Taylor series maybe came from, so that when you use it, you're not completely confused about what the heck it is. Okay, so I'm going to do what I'm going to try to construct a series for sine of x without any knowledge of what a Taylor series actually is. So I have no clue what a Taylor series is. I'm going to just construct a series for the sine of x knowing what I know about series. So let's first understand, and I'm going to construct what the books like to call a power series. A power series just means a polynomial, the kind of series we've been talking about, where x's are raised to powers and we basically have a big polynomial. That's what we call a power series. Okay, so if I want to write a series for the sine of x, that means I want to write a series that is made up of x's to powers. So I want to figure out what that series should look like. So I want the sine of x to be written as a series that would say, I would have a first term. We're going to call that first term a sub 0. And then my next term would potentially be another a times an x raised to the first. Then I would have another potential different coefficient times x to the second, plus another potential coefficient times x to the third, and so on. In fact, I'm actually going to write a few more terms here. Oops. Get rid of that. So let me write a few more terms. So all I'm writing down here is, this is what a general series would look like. This is what all of my series so far look like. I sometimes have x replaced with something else, but for every series that I have, like when I have 1 over 1 minus x, I have 1 plus x squared plus x to the third and so on. So in this particular case, my a sub 0 is 1. My a sub 1 is also 1. All of my a's in this case are 1. And my x's go on. Now let's say I had something else, like if this is minus 3x. Now I have 1 plus 3x plus 9x squared plus 27x to the third. Now my a sub 0 would be 1. My a sub 1 would be 3. My a sub 2 would be 9. My a sub 3 would be 27. So you have to differentiate between all these different a's because the coefficient of each term could be different. Like in this case, 1, 3, 9, 27. So that's why we have an a sub 0, a sub 1, a sub 2, because that coefficient is going to potentially change as I go through each term. Okay, so I have my goal. My goal is to figure out what this is to figure out what all these values are for a and how this ends up looking in the end. So I'm going to use the fact that if I take the derivative of a series, both sides, I will be creating a new series that's legitimate. So I'm going to use this in this yellow box. I'm going to keep going back to it. I'm going to be trying to figure out what all these coefficients are. So, but I'm going to start by saying, I'm going to write this again because I want to keep going back up to here and putting it in, but I'm going to write out the series again. Sorry, I should have had this like typed up maybe, but so I'm saying that the series for sine of x equals this. That's nothing. Go one more. Okay. Well, that's the series for sine. Let's take the derivative of it. Let's take the derivative of both sides and see what that gets us. Oh, wait, no. Okay, never mind. Woof, back up. Okay, so if this is the series for sine, this series alone can help me figure out what a sub 0 should be, and here's how. All right, I didn't mention this yet. So when I talk about the function and the series, we understand that they overlap each other if I were to graph them. If I graph the sine of x and I can graph the series for sine of x, their graphs are identical, at least on a certain interval. So if I graph sine of x, whatever its series is, should look identical, at least for a while. So maybe it ends up falling away at a certain point, but at least from -1 to 1, and maybe even further, we should have a basically exact match if I were to graph all the terms of the series and I were to graph sine of x. Well, the strength of that matching is the strongest at the center of the interval of convergence. So let's say we only know that these will converge from -1 to 1 or whatever. The center of that interval convergence is going to be at x equals 0. So right now, at x equals 0, sine of x is going to match its series exactly. We're guaranteed that strength because that is the center of the interval of convergence. So what that means is, if I look at this, when x equals 0, these two should be an exact match. So if I plug 0 into both sides, these should be an exact match. So that means if I plug 0 into this side, plug in x equals 0, and plug in x equals 0, what am I going to get? I'm going to get the sine of 0 is 0. And over here, when I plug in x to be 0, all of these terms are going to cancel with the exception of a sub 0. Guess what? That's the value of a sub 0. I just found one of the values of the coefficients in the big series I'm trying to find. I just found out what a sub 0 is. So I can take out a sub 0 and replace it with what I know it is, 0. I'm going to keep going. At any time, if you want to pause and go back and listen again, that would be wonderful. So what does it mean to keep going? To keep going means I'm now going to take the derivative of each side of this, because if you just watch for a minute, it's going to help me get more terms. And I'm always allowed to take the derivative of both sides of some crazy thing, of an equation. So the derivative of sine is cosine, and that's going to equal the derivative of this side. So let's take the derivative. The derivative of a sub 0, so this is just a constant, is 0. The derivative of a constant times x is just the constant. The derivative of this is going to be 2 times a sub 2, x to the first. The derivative of this will be 3, a sub 3, x to the second. The derivative of this will be 4, a sub 4, x to the third. The derivative of this will be 5, a sub 5, x to the fourth. The derivative of this will be 6, a sub 6, x to the fifth, and so on. So now I've just created a series for cosine based on this hypothetical series for sine that I'm trying to find. And the reason I'm doing it is I'm going to do this again. I'm going to say, okay, well, if I took the derivative of this series to get this one, this cosine and this series will also converge on the same interval of convergence, and that match will be close, or will be exact at x equals 0. So I can plug x equals 0 into both sides of this equation and see if that gets me anything. Plugging 0 into the cosine of x gives me 1. Plugging 0 into this equation means every term cancels except for that. So I just found out what a sub 1 is. I can now go back to here and I can get rid of a sub 1, and I can replace a sub 1 with the number 1. So I am methodically, step by step, building a series. That's what I'm doing here. I am building a series for sine based on its setup and based on the fact that when I graph this function and this series, their match will be exact at the origin. Maybe not as I move away from the origin, but that the match will be exact at the origin. The function and the series will equal the same y value. So I can plug 0 in for x into both sides and have a legitimate answer. So I'm just kind of reviewing now. So I still got to go. I got a long ways to go. what I'm trying to do now is work step by step to find out what my coefficients of x are in this series. I've found 2 of them. I found the first one by knowing what sine equals and plugging in 0 for both sides, being left with this. Then I took the derivative of this series to give me another legit series that I can plug 0 into both sides for and end up with another legitimate answer that the cosine of 0 will equal this side when 0 is plugged in, which leaves me with cosine of 0 being 1 equaling just this a sub 1 that's left. So what am I going to do next? Any ideas? I'm going to take the derivative again. So I'm going to work through again. I'm going to take the derivative from here. So the derivative of cosine is negative sine. And I'm going to take the derivative of this line. So the derivative of a sub 1 is just 0. I could write that if we want, but I'm not going to. And then I'm going to take the derivative of this. So 2a sub 2x, the derivative is just 2a sub 2. The derivative here, I take the 2 times this, so I'm going to have 6a sub 3x. This I'm going to have 12a sub 4x squared. Here I'm going to have 20a sub 5x to the third and 30a sub 6x to the fourth. And again, that would go on. And then I'm going to take this. I'm going to plug 0 into both sides for x and see what I get. The negative sign of 0 is 0. Plug 0 in for all of these x's, and I'm just left with 2a sub 2. So a sub 2 will equal 0. I can go back up, and now I can replace a sub 2 with what I know a sub 2 is. 0. I'll get rid of that in a second. Okay, I'm going to do it again. Take the derivative again. So the derivative of negative sine is negative cosine. The derivative of this term is 0. If I were you, I would pause it and I would take the derivatives yourself, just so that you kind of understand what we're doing as opposed to just watching. Or try to think it in your head before I write it down. So derivative of this is 0. Derivative of this is 6a sub 3. And then 24a sub 4. 60a sub 5x. Whoops, I forgot my x's, didn't I? 0. Sorry, this has an x to the first in it. 60a sub 5x squared. 120a sub 6x to the third, and so on. Hopefully you're getting this pattern now. I'm just doing the same thing now. I'm going to plug in 0. I don't know ahead of time what I'm going to get. This is just, I'm seeing what I get each time. So if I plug in 0 for x, the negative cosine of 0 will be negative 1. And on the right, when I plug in 0 for x, every term cancels other than 6a sub 3. Ooh, so what will a sub 3 equal? Negative 1/6. Different. Now we're getting into something a little bit different. Instead of all these 1s and 0s, I got an actual interesting number. Whoops, negative 1/6 for a sub 3. So let's go back up. Let's erase a sub 3. And let's put in negative 1/6. Right now, this series for sine looks completely random. It looks like I don't have anything that I'd ever be able to find a pattern for. But that would be wrong. We're going to have a pattern. We just don't know it yet. Oh my God, we have to do this again. Derivative time. Take the derivative of negative cosine and we get sine. Take the derivative, we get 0. We get 24a sub 4. We get 120a sub 5x. We get, 360a sub 6x squared, and so on. I'm going to plug in x equals 0 into both sides. The sine of 0 is 0. I'm going to get 0 equals 24a sub 4. So a sub 4 equals 0. Go up here and let's get rid of a sub 4. And let's put in 0. All right, let's get one more, so at least we have one more term. We'll be able to maybe see a pattern after that. Oops. So take the derivative again. Cosine of x equals 0. 120 a to the 5th plus 720a sub 6x plus blah, blah, blah. Let's plug 0 into both sides. Cosine of 0 is 1. Plug 0 into here, I get 120a sub 5. So a sub 5 equals 1 over 120. I can go put that in for a sub 5. Okay, so at this point, you are immensely bored and completely checked out. But what I'm hoping that you've seen is we have just built a series for sine. We don't know the rest of the terms yet, and it looks like there's no pattern. But let's look a little bit more closely. So I'm going to erase this stuff. So I just figured out that the series for sine is this. Let's write this out a little nicer. The series for sine is, I'm going to get rid of the zeros, no need to keep them in there, is going to be x minus, I'm going to write this as x to the 3rd over 6 plus x to the 5th over 120. Okay, what would the next term be? Well, definitely it'd be minus, definitely it would be x to the 7th, but what would be under there? I see no pattern. I don't see a multiplier. Obviously, this is over 1. It's not like I can multiply by 6. So what the heck is the pattern? I would love for us all to be together and be like, the first person to figure out the pattern gets a lollipop. But we're not together. So I will have to just spoil it for you. Guess what? These bottom numbers are factorials of the power of x on the top. Believe it or not, 1 is 1 factorial, 6 is 3 factorial, 120 is 5 factorial. Oh my God, that's amazing. Factorials actually play a part in trig and Taylor series. It's so crazy. So this is the same as 3 times 2 times 1. Yep, that's 6. This is 5 times 4 times 3 times 2 times 1. Check it. That's 120. So what's going to go under here? 7 factorial, which I can get it. I don't have my calculator on me at this point. But this, well, fine. I'll get it figured out. Will be 5,040, which is the same as 7 factorial. What will the next one be? X to the 9th over whatever 9 factorial is, and so on. This is the series for sine. Oh my gosh. So the series for sine, if I'm going to be, I don't want to leave it as the expanded form. I want to put the factorials under here. How about that general term? The general term then is the series or the sum of -1 to the n or something, because these powers alternate. So we're going to have that alternator. X to the, do you remember how to write odd numbered powers? It's going to be 2n plus 1 over 2n plus 1 factorial. N is going to start at 0. Because 0 will give me x to the 1st, 0 will give me 1 factorial, 0 will make this positive. And there it is. That is the series for the sine of x. Holy crap. I want you to do 2 things now. I want you to find out, number 1, what is the series for the sine of 2x? We can get that. We can use substitution to find it out. Number 2, what is the series for the cosine of x? We can do that as well, because we can take the derivative of this and get the series for cosine. That is your assignment for today. We're going to pick up on this tomorrow, but I'm going to go ahead and, because I'm here and in the groove, I'm going to go ahead and do these two. I'm going to do the answers to them now. So try these on your own and see if you get the right thing, and then we'll pick up again tomorrow. So I know I didn't even mention the word Taylor series yet, but this is definitely enough for one day. So tomorrow we'll move on and talk about how to actually do all of this without doing everything that we just did. That last 25 minutes of your life was a lead up, was a way to figure out what sine is, but there are shortcuts so we don't have to do that every single time. But let's end it here with understanding this is the series for sine, this is the general term, and now we have it. Now we can write it down and we can include it with inverse tan. We don't have to do it from scratch anymore. We know what the series for sine is. So I'm going to go ahead and do these right now. I would pause it, try them yourself, and then come back. Okay, so the answer for number 1, the sine of 2x. All I got to do is replace all my x's with 2x. So it's going to be 2x minus 2x to the third over 3 factorial plus 2x to the fifth over 5 factorial, and so on. General term is just the same as it is up here, my -1 to the n, but now replace x with, 2x. So that substitution is really easy, especially if I already have a general term. I already had the general term, so just replace the x in the general term with 2x. That's it. Okay, now for the more difficult one. What is the series for cosine of x? So to find the series for cosine of x, I'm going to just use the series for sine of x, and I'm going to take the derivatives. So let's see what I get. So the derivative of sine is cosine. The derivative of x is 1. The derivative of this is minus 3x squared over 3 factorial plus 5x to the fourth over 5 factorial minus 7x to the sixth over 7 factorial, and so on. So let's reduce this and see what we actually have here. So the series for cosine is 1 minus, remember 3 factorial is 3 times 2. 3 times 2 times 1. So the 3's are going to cancel. So I'm going to be left with x squared over the 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. So these 5's will cancel. And I'll have x to the fourth over 4 factorial. Same thing here. Get that term, 7, 6, 5, 4, 3, 2, 1. 7's cancel. And I'm left with 6 factorial. Now do you see the nice pattern, and can you write the general term? So I'm still going to have an alternator, but my x is going to be raised to powers of 2n divided by 2n factorial, the evens, not the odds. Let's check and see where my n should start. Can I start with 0? Sorry, looks like I can, right? If I put 0 in, I get 1 up here, and I'm all good. All right, so this might cause a problem. You might think, wait a second, I can't have a 0 factorial. Oops. So we didn't talk about that, but maybe back in the day, so you might be like, wait, how can I start at 0? I'd have a 0 factorial on the bottom. Well, guess what? 0 factorial equals 1. It's a rule. It's something we just all agree upon, because otherwise it really screws some things up. So when you have 0 factorial, that is the same thing as just 1, just like 1 factorial is the same thing as 1. So if I plug 0 in here and I end up with 0 factorial, that's okay. It's all fine. Okay, well, I'm tired. So there you go. We will meet back up tomorrow. We will not have we could have a quick check tomorrow. Interesting. Yeah, maybe we will. That'd be fun. Maybe I can just give you like a cosine of 3x or something and make sure you're okay with writing that. Or how about a cosine of x minus 1? What would that look like? Subtracting 1 from both sides. Yeah, we'll probably start with that. All right, have a great day.